iC-Haus Integrated Circuits.
Greetings, dear audience. My name is Stefan. I am Sales and Application Engineer for image sensor products. To ease your development of triangulation sensors and many other applications, I will present how you get started with a CMOS linear image sensor from the iC-LFH series. The high resolution of 2000 dots per inch makes them ideal for scanning applications, like fingerprint scanners or handheld line scanners, those for optical character recognition. A good use case is also distance measurements using triangulation. So what do we need? The chip itself on the sensor module. The sensor module is the LFH1M. It can carry different versions of the iC-LFH. And we need a controller board to hook everything up to, the LFH1D. It comes with a cable to connect to the sensor module. For this demonstration, I went for the rather long iC-LFH1024. The number 1024 stands for the amount of pixels built in. The other ones are shorter, so less pixels, but same resolution. Available are 960, 640 and 320 pixels. The exact name of the long chip's sensor module is iC-LFH1024 EVAL LFH1M. Also important, the iC-LFH EVAL LFH1D controller board will generate all control signals needed. We just need an oscilloscope to display the output of each pixel. Fastest signal will be the pixel clock. iC-LFH allows for up to 5 MHz pixel clock. So a simple real-time oscilloscope with 20 MHz analog bandwidth will work. 2 channels would be minimum. 4 channels are better to view all signals at the same time. For the power supply, we need 5 volts DC, delivering up to 500 milliamps for the controller board. Now, let's configure the LFH1D control board. First of all, connect the control board to the sensor module. This is what the ribbon cable is for. For starters, we will just supply everything with the same 5 volts. So jumper 5, JP5 is closed, and jumper JP7 is on the 5 volt VDD position. Analog ground AGND is connected to GND at JP6, with JP6 being closed. The chip on the sensor module is model 1024, so the rotary switch S4, which is labeled LFH type, goes to 4, here up north. Now the control board knows how many pixels make up a frame and when to start a new integration for the next frame. If your application needs either a shorter sensor or less pixels, you can of course go for one of the 3 other chip variants. Those 3 terminals here at the bottom, at the lower end of the PCB, are the signals generated by the control board. I hooked them up to the oscilloscope to see how it controls the iC-LFH. But most important is the signal where we read out the individual pixels. This is at terminal A out. Here the voltage changes according to the amount of light that was captured by the pixel during the integration phase. So everything static is connected. Let's define some defaults with the other jumpers and other switches. Jumpers RES1 and RES0 go to their 0 position. The iC-LFH will operate with its native resolution then, 2000 pixels per inch. That is the highest resolution available. For the iC-LFH1024, this will result in 1024 pixels per frame. Jumper B and A is in its AVG position. For the highest resolution, there is no difference between AVG, averaging, and the binning BN position. But for the reduced resolutions, the pixels will either be combined in binning mode, BN, or the pixels will be averaged, AVG. I'll demonstrate this later. Now to the switches that control the readout settings. S2, down here, is a pixel clock. How fast do we read each pixel? Position 0 is the default I'll start with. Position 0 is the slowest clock, 100 kHz, and the dial goes all the way up to 5 MHz. That is the fastest that the iC-LFH series is capable of. S3 is the global shutter. Position 0 is again my default. This will keep the shutter permanently open. Light will be continuously captured by all pixels. Other positions of S3 will open the shutter for shorter amounts of time. So operation modes were selected and some default settings were defined. I can now power on the control board. The power supply is at 5 volt, and as soon as I make the electrical connection, the signals from the control board and the output of the iC-LFH become visible on the oscilloscope. Now we see 3 signals generated by the control board. Channel 1 with the yellow trace is a pixel clock, just a continuously clocking signal. Channel 2 with a cyan or light bluish color is the start integration pulse. The time between 2 of those pulses here and there is what we call a frame. All the 1024 pixels of this chip are read out within a frame. This is the channel I am triggering the scope with. Channel 3, violet in color, is the signal for the global shutter. Right now, permanently open and a flat line here at the bottom. Last but not least, channel 4 in green, the readout of the pixels coming from terminal A out of the control board. Here you see that after the start integration signal, the iC-LFH outputs its lowest possible pixel voltage. This is basically our completely dark baseline. On the 17th rise of the clock, the voltage at A out switches to the voltage from the first pixel. Each rising edge of the clock from now on shifts over to the next pixel. After a new start integration pulse, the procedure restarts. As you see, all pixels put out the same voltage. We have a flat line extending between our phases of dark current. The amplitude of about 4.8 volts between the dark minimum and the pixels indicates that the sensor is fully saturated with light. It seems pretty bright in the video studio for this chip. With those general remarks out of the way, I can now tune the settings to get a usable signal that is not saturated. For a quick test, I can just cover the sensor with my hand to see if it reacts at all. Yes, the signal goes down for every pixel, and the different pixels measure different amounts of light. So the straight line from the brightness saturation becomes curvy. As I remove my hand again, the signal goes back to saturation. Let's change the frequency of the pixel clock with the rotary switch S2. As the shutter is permanently open, currently light is collected the whole time between 2 start integration signals. When the clock frequency is increased, the time frame between 2 integration signals becomes shorter, so less light should be collected. Position 0 is the slowest, 100 kHz, so I'll dial it up to see when it goes out of saturation. So I dialed now half of the possible positions. Still no decrease in signal, so there's still saturation. And only the start integration pulses appear more often on the oscilloscope. So let's continue to increase the frequency. No reduction. Yeah, now I went full circle. I am back to the 100 kHz setting. So even with the fastest pixel clock of 5 MHz, the studio lighting is too bright. So I'll set S2 back to 5 MHz, that is position F, directly next to 0. And to get more details on the scope, I will change the time base. Zooming in just on a single frame, so with 1024 pixels. And now I'll use the global shutter to limit the exposure within one frame. This should finally give us a good, not saturated signal on our green trace. As I turn the shutter switch from 0 to 1, the exposure time is cut in half. The violet trace of the DIS terminal is now high for half of the time. Also, the signal height dropped significantly. The other two positions available make the exposure longer again, 2 and 3. Now the signal is again saturated. So back to 1 to have a useful signal and a fast readout. In an application with a dedicated light source, one can pulse the light source and synchronize it to the time the global shutter is open. This then would reduce the influence of ambient light. I am just using ambient light as my light source today. So the easiest thing to do to test the functionality is to cast a shadow on the sensor. If I place this little wire across the sensor, immediately there's a dip in the green signal trace. And of course, when I move the wire to one end of the sensor, the dip on the scope trace moves to one end of the frame too. This is quite an easy test, but in most applications, a point of light or maybe a line should be detected. I can easily mimic this scenario with this 2 mm pinhole I brought with me, though I now have to be more exact in positioning it. A slit would be easier. Let's see if I can get a signal. Yes, this is beautiful. Anyways, now there's only one positive peak on the green signal trace. Obviously, the peak moves corresponding to the position of the pinhole. This is a more realistic depiction of a triangulation signal. And to show off a more complex pattern, I have a transparent ruler with me. And if I place this ruler over the sensor, we see various dips in the ambient light. Those dips are the shadows cast by the distance markers. Last to present today is the binning feature to increase the sensitivity. This, I'll have to use it in conjunction with the lower resolution feature. So first, I change the jumpers to a lower resolution. Jumper RES0 goes to its 1 position. Now, always 2 neighboring pixels are used together. The frame length got shorter, only 512 pixels now. This also reduced the integration time, so the amount of light captured by each pixel went down. Jumper BNA is still on averaging, so the average is put out. And if I change the jumper now to its BN binning position, the 2 neighboring pixels are added together instead of averaged. And as a result, the signal increased again, nearly to where it was before. Binning allows for more signal from the same brightness light source, as long as a spot of light is big enough to hit all the pixels that are forming one bin together. Especially spectroscopy applications can profit from higher sensitivity by binning pixels together. Now, you should have a head start in developing your linear image sensor application. More details are available on our website, iC-HausVideo.com. So long and goodbye.
iC-House. Integrated circuits.